All right, we're going to continue with our lesson from yesterday. Yesterday we were looking at using the first derivative to calculate max and mins. So this second video just continues with that, and we're going to get a little bit more specific on terminology and look at extreme values and that sort of thing. So the first thing you can see is on this picture, we still have max and mins where our slope is equal to 0. So for example, this minimum has a slope of 0 at the bottom, so that's why it's a minimum. This maximum, the same thing. But we also call that one an absolute maximum because it's the overall highest portion of the graph. This minimum that we did first isn't an absolute minimum because there is this lower portion on the graph down below it. So the absolute is pretty simple. It's just dealing with the highest and the lowest overall of the graph, or kind of like what the range of the graph would be. So we're going to see that, but we also see that there's issues where we have something like this that has a slope of 0, but it's not a max or a min. So we'll kind of clarify a few things that we did yesterday, and then this will lead to what our next lesson on the second derivative will be all about. So the first thing in terms of terminology, we call a max or min in just in one specific location, like this point D. We would call that a relative or a local minimum. Those mean the same thing. So if it's just at a certain section of the graph, it's a max or min, or a relative local max or min. If it's the overall highest point, like this point E, then it would be an absolute max. And my point G got cut off on this picture. Point G was down here, so that would be our absolute minimum. So our maxes and mins depend on what the overall highest and lowest portion of the graphs are. A turning point is when we say our slope changes from positive to negative or negative to positive. So you can see on this graph, we have a turning point at all of our max and min locations, so B, D, E, and G. C is also a turning point, but what's different about it is our slope doesn't become 0. So you can see for B and D, these maximums all have a slope of 0. At point C, our slope is actually infinite. They're kind of going up like a peak of a mountain. So that one, we actually call that one a cusp. A cusp is a sort of a fancy name for a maximum where the slope isn't 0, but it's infinite instead. We're not going to worry about that so much for this course. That's more of a university level. But just to be aware that it doesn't have to be a max or min. And a stationary point is where we get a slope of 0. But again, that doesn't necessarily have to be a max or min. You can see at point F, we also have a slope of 0, but it's not a max or a min. So not all slopes are 0 that are 0 give you max or mins. That was our point F. And not all max and mins have a 0 slope, kind of like our point C. So those are just kind of special cases. In most cases, we're going to deal regular graphs that have max and mins, and we don't worry about the cusps and things like that. So what we got to remember is when we're testing these things, we want to test to see what's happening to the slopes. So if we had a test point and we went from positive to negative, obviously that would be a minimum, right? Our slope is changing from positive to negative. Oops, I got that backwards, sorry. From negative to positive would be our minimum. So let's switch that. And then if I did a point that went from positive to negative, that would be our maximum. And just like we just said, if we had a point where it doesn't change, that would be a stationary point, but it's not going to be a max or a min. And we'll do more of those tomorrow. So for a graph that has an absolute max or min or absolute location, again, we're just sort of dealing with the overall graph itself. So typically it's sort of like dealing with the range. So if you had a graph something like this, that would be our absolute maximum, and down here would be our absolute minimum. So what we got to add to what we did yesterday is we still want to calculate where the slope is equal to 0. That's still going to be our critical locations for maxes and mins and things like that. But we also got to be aware of anywhere where the slope would be infinite or undefined. So that's also important, because if we have asymptote lines or cusps or anything like that, we got to also deal with those. We still want to check the slope on either side of those points. And we also want to examine the endpoints. When I say examine the endpoints, typically we just want to figure out what the coordinates are. So if we have a restricted domain, we want to figure out what are those coordinates, because that could affect our absolute max and min. So we really just do the same thing we normally do, but we just kind of chop our domain point. So for this one, let's go through this. So we have a fourth degree graph, so we know it should look like a W. We're looking for the absolute minimum or maximums of this graph, and you can see our domain has been restricted between -3 and +2. So we could still do our x and y intercepts like we did yesterday, but we don't typically have to worry about it till the end because sometimes we might not need them, sometimes we will need them. So in this case, let's skip the intercepts. We have no asymptotes, so we really can move right on to our derivative. So if we do the derivative of this equation, we'll get 4x cubed minus 4x. If we take that derivative and make it equal to 0, and let's factor out a 4x, and we can factor the x squared minus 1 even further into +1 minus 1, and now we can see that we have three critical values. We got 0, 1, and -1, right? Remember the 0 is for that first x, and then we got all our two factors to get the other two. So in this case, those are our three critical values. So when we do our number line, we want to include 0, 1, and -1, but you can see we also have our endpoints at -3 and 2. So in terms of doing our testing, those don't affect anything, but just kind of make sure we don't go beyond those. So we've got our 4 intervals that we want to test. So we want to test this between -3 and -1 zone first. So let's plug in a -2, and you can plug it in any of the first derivative equations, but it's probably the simplest if you put it in the factored version, because you don't really need a calculator for that. Remember, we don't care what the number is, we just want to know whether it's positive or negative. So if we put a -2 in there, you can see we'd have 4 times -2 would be -8, -2 times minus -1 would be -3, and then -2 plus 1 would be -1. So we have a negative times negative times negative. That would give us a negative slope. So if we do the same thing with -1/2, we'd get -2, -1.5, but now we'd have positive 0.5. So that one would give us a positive final answer. If we do it with +1/2, we'll have positive, negative, positive, which would be back to negative. And if we do it with something like 1.5, we'd have positive, 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 which would give us a positive answer. So just from that, now we know we have slope changes, so we should see that in our first interval, we're going from negative slope to positive slope, so this should be a minimum. Then we're going positive to negative, so that one should be a maximum, and then negative to positive once again would be a minimum. So we pretty much have everything figured out for the graph. The only thing we would like to have is our coordinates. So let's figure out our endpoint coordinates. So if we plug -3, and remember these, you always want to go back to the original, plug in -3 into that equation, we get 79. If we plug our -1 into that equation, that'll give us -1, that'll give us 14. If we plug 0 into that equation, sorry, -1, 15, not 14. And we plug 0 into that equation, that gives us 16. Plug in +1, it also gives us 15. And if we plug in our +2, we'll get 16, 32, take away 8 is 24, I think, if I did that right in my head. So that should be our 5 key coordinates. Now we should be able to sketch out the graph. So we have -3, 79, so we have a really high coordinate up here. -1, 15 would be somewhere in the middle. 0, 16 a bit higher. 1, 15 a little bit lower. And then 2, 24, something like that. So just from those max and mins, we should be able to get an idea what our graph would look like. So you can see that we have a absolute max is now at our -379, and our absolute minimum is either of the two smaller ones. Okay, so there's the answers of the previous question. Looks like we did everything right, so let's move on. So here we have a rational graph. So we got 16 divided by x. So be careful with these. We can see that x can't equal 0. So that'll become a critical point that we also have to worry about for this question. So again, x, y-intercepts may or may not be important, so we won't worry about those. Let's just go right to our first derivative. And if we think of derivative of x squared is 2x, and if we think of 16 over x, if you write it as 16x to the negative 1, that would give us negative 16x to the negative 2, but I'm going to write it as negative 16 over x squared. So now if we make that equal to 0, we can move the 16 over to the other side, so that'd make it positive 16. And we can bring the x squared up, divide by 2, and cube root it will give us an answer of 2. So for this question, if there were no other restrictions, we'd have something going on at 0, and then we'd have a max or min likely at 2. So if we were to do our test points, those would be our only 2 points. But because we have a restricted domain again, we're only going to go between 1 and 4. So that means we only have to worry about 1, our max or min at 2, and then our other endpoint at 4. So the question becomes a little bit easier because we don't have to worry about that 0 in this case. So again, let's do our couple test points. Let's put in a 1.5, and it doesn't matter which version we put it in. Let's just go into this equation. Plug in 1.5, that'll give us a negative value. Plug in a 3, that'll give us a positive value. So we can see that we have a minimum at 2. And if we go back to the original equation, that would be 216. And let's do our endpoints. So if we plug in a 1, we would get 17. And if we plug in a 4, that'll give us 20. So that should be it. So based on this graph, if we were to sketch out this graph, we would have those 3 coordinates. So 1, 17, 2, 16, and 4, 20. So our graph would look kind of like that if we cut off our 2 endpoints. And it would be something like that. Okay. So that's it for that question. Before, maybe let's just look at it, what would happen if it wasn't at positive 1. Let's suppose it was at negative 1. So the only thing that would change with our graph is we would have, instead of it being at positive 1, we would have 0 as being a key point, and then we would go down to negative 1. So we would have to just extend our test points. So we already got 0 to negative 2 as a negative slope. We would test from negative 1 to 0. In this case, if we plug that in, that would give us a negative slope as well. So you can see it's not a max or a min. The 0 would give us our asymptote line. And if we plugged in negative 1 as an endpoint this time, negative 1 would give us negative 15. So we would just get our coordinate down here somewhere. So because that's an asymptote line, the graph would just go downwards towards that asymptote line, and then it would continue upwards towards that asymptote line. So if the 0 is important, we got to take account of it as our test point. If it's not, we can ignore it and just do it like a normal question. And there was our answers, and we have one more example. So let's go through one more example. This one is another cubic type of equation, except I want to know the stationary points. So that could be max or mins, but the key thing is where the slope is 0. It's asking for the intervals of increase and decrease, so where the slopes are positive or negative, and we want to sketch the curve. So this one's written in factored form, which helps a little bit, especially when we're dealing with our intercepts. So this one, let's list our x-intercepts this time. So in this case, our x-intercepts are at negative 1 and 2. So that helps. Our y-intercept would be when x is 0, so that would give us 1 times negative 2. And if we do our derivative this time, our derivative is going to be a little bit tougher because it's written in factored form. We're going to have to do a product chain combo. So if our f is x plus 1 squared, that derivative using a chain rule would be 2 times x plus 1 to the 1 times 1. And our g is just x minus 2, so that derivative would just be 1. So if we do our derivative, our product rule derivative, so let's write it as y prime will equal, multiply those two, so 2 times x plus 1 times x minus 2, plus those two. And remember, with these combos, we usually just common factor, so let's take out an x plus 1, and our leftover part would be 2 times x minus 2, and one more x plus 1 left over. And if we simplify that square brackets, we would get 2x minus 4 plus x minus 1, x plus 1, and that would simplify to 3x minus 3. So we should be able to simplify. We can take out a 3 out of that, so we'd have 3 times x minus 1, and our original x plus 1 that we had out front. That would just carry all the way down. So that should be our factored version, and we're going to use that version for all of our test points. But from there, we can see that our key critical points are going to be at 1 and -1. So let's go to our test line. So we know that we have 1 and -1. We don't have any endpoints this time, so we don't have to worry about that. We do have our x and y intercepts, which will help for graphing. And other than that, we should be good to go. So let's plug our test points into this bottom equation. And again, it'll help us to figure out the signs. So if we plug a -2 in, you'd have 3 times -3 times -1, so that'll give us a positive. Plug in a 0 would give us 3 times -1 times +1, which would give us negative. Plug in a 2 would give us positives for all of them. So we can see that we have a maximum at -1, and we should have a minimum at +1. So let's plug those back into our original equation to get our coordinates. So if we plug -1 in there, we'd get 0 for our y coordinate. Plug in +1, that would give us 2 squared, which is 4, times -1 would be -4. So we should be good. We have everything figured out. So our stationary points, where our slope is 0, that's our 2 max and min locations. So there's our stationary points. Our intervals of increase and decrease, that would come from our number line. So we can see that our graph is increasing where their slope is positive, so that'll be from -infinity to -1, and from 1 to +infinity, and we're decreasing from -1 to 1. So our last thing that we want to do is sketch out our graph, and I think we should have everything we need. We've got our max and mins, so let's label those at -1, 0. That's a maximum, so I'm going to put a little curve on there so I remember it's a maximum. 1 and -4 would be a minimum, so let's put another little curve like that. We have our x-intercepts at -1 and 2, and we had a y-intercept at -2, and that should be it. So we should see that it's a cubic graph, so it should go up to this maximum, through the y-intercept, through the minimum, and back up again. We don't have any absolute value max or mins in this case because the graph went on and on forever in both directions. So we would just have our local max and mins that we determined earlier. Okay, so tomorrow what we're going to do is we're going to figure out what the second derivative does, and that'll help us give us a little bit more information with these graphs, and it'll actually make a little bit of the work that we did today a bit easier as well. So we'll look at that tomorrow, and that'll help us finish off graphing, and then we're almost done the unit. So that's all for now.